White dwarfs are the leftover remnants from main sequence stars like our sun. After they have gone through all of the fuel in their core, they blow it out as red giants, and then they blow off all of their outer layers, and you're left with just the hot, bright core of the star, just out in space. And this is a white dwarf. And eventually this thing will cool down to the background temperature of the universe, although that will take a very long time. It was long assumed that it was just this ball of leftover elements floating in space, slowly cooling down. It was dead. But of course, things are more complicated than we could ever assume. And it appears that white dwarfs are not dead after all. And in fact, their temperatures seem to stall out and they don't cool down, sometimes for billions and billions of years. And this has always been a puzzle, which maybe has been finally solved. So my guest today is Dr. Simon Blouin. He is a postdoctoral fellow at the University of Victoria. He is part of a team that has been doing a ton of research into white dwarfs, and we describe his research as well as just like a whole bunch of other questions that I have about white dwarfs. So you know how this rolls. Enjoy this fascinating conversation with Dr. Simon Blouin. Simon, if you could fly through space to a just standard white dwarf star and go into orbit around it and maybe look at it from the kind of distance that would be not deadly, what would you see? And I'm assuming you'd need sunglasses.
What would you see? Probably not that much, honestly. So we think that white dwarfs, most of them have a pretty homogeneous atmosphere, so that's the only region that we see. So when a white dwarf is at the beginning of its life and it's quite hot, then it will be mostly white or bluish, and that's when you have to worry about UV radiation. But actually, most white dwarfs are pretty cool. So temperatures of the order of that of the sun or even cooler. And so then the color would be similar to that of the sun, and you don't really have to worry about UV radiation in that case. So what happens with white dwarfs, I guess we'll go more into that, but they just cool down for all their lives. But the cooler they get, the slower they cool down. So you have an accumulation of white dwarfs at cooler temperatures. And in fact, white dwarf is a bit of a misnomer in this sense because, most of them are actually not white, but rather more yellowish because they're quite cool.
Okay. Now, but when I think about the kinds of observations that have been done of the sun in different wavelengths, and especially once you're starting to filter out the bright light from the sun and you're able to see sunspots, you're seeing different granulations on the surface of the sun. You're seeing the fainter atmosphere and the corona around it. And so if you could put the right filters in front of your eyes, if you could put the right kinds of instruments to look at that white dwarf, how would it sort of compare to your experience with looking at a star?
So most white dwarfs, so when you get to cooler temperature, they have convection in their surface layers. And so if you're looking at the right wavelengths and with the right filters, you could probably see similar features that we see at the surface of the sun for sure. And then, about 20% of white dwarfs also have strong observable magnetic fields. And so it's possible that for many of them, you could have some star spots. So very analogous to what we have for the sun. From Earth, the only way we can see those star spots is basically you have, if you take a time series of the brightness of the star, you can see regular dips for some magnetic white dwarfs. And then it's like a darker spot that's rotating on the surface of the star is rotating, and we see this dark spot coming and going away. So that could be another feature that you could see from up close.
And we always talk about that final step. In theory, once these things have cooled down to the background temperature of the universe, they freeze up and become like the universe's largest diamond. So how would that perspective change over time from like the most hot white dwarfs, the ones that are just brand new, through that lifetime? How would that settle down the way they change how they look?
So first thing, I just need to push back on the diamond analogy because this is
great.
Something that's been annoying me for
Please do. This is
years.
it.
So the what you have inside the white dwarf, so the core, which makes up 99% of the mass, is carbon and oxygen, roughly equal amounts. It's not clear exactly what's the mixture, but they're both. So a diamond is pure carbon. And inside a white dwarf, you have roughly 50% oxygen, 50% carbon. So that's a first important difference. And second important difference with respect to a diamond is that it's true, and I guess we'll talk more about it, but that the interior freezes into a solid state. But it's a different crystalline structure than a diamond. So the way the ions are arranged, so you have like a regular lattice structure, it's just a different configuration. And then the nature of matter inside of white dwarf is very different than what you have with a diamond. So the densities are like 1 ton per cubic centimeter. So it's really a different thing. So it is a big crystal. So crystal is the right word, but it's not because there's carbon and it's a crystal that it's automatically a diamond. So just one thing to keep in mind. Then
But like, what kind of crystal? I'm sorry, like if you had I mean, is it like, is the interior of a white dwarf to a diamond like magnetic hydrogen in the center of Jupiter is to hydrogen gas? Like high pressure makes atoms do funny things?
Yeah. How would I compare? I mean, so it is a plasma. So you have carbon ions and oxygen ions that are stripped bare of their electrons. So you have a sea of electrons. And in this background, the ions, they are arranged like on a regular lattice structure. Then how would this actually look like? I don't know. Like we know on the microscopic level how things are arranged, like how it would look like visually, that kind of thing. I have absolutely no idea. That being said, the temperature is in the millions of kelvins. So, I mean, it would be quite bright.
Yeah. Yes. But I guess I'm just wondering, like once it cooled down, because you're saying it's a plasma, but if it has cooled down to the background temperature of the universe, it is no longer a plasma.
Oh, yeah.
It is a crystal.
So so the crystallization happens way before you reach those low temperatures. So what happens is that to decide whether a system goes from the liquid to the solid phase, you have to consider two things: the temperature and the density. And so if you're denser, you can crystallize at quite high temperatures. And in fact, our white dwarfs, they crystallize at millions of degrees. So you're still a plasma. So often people have this picture that plasma is necessarily fluid, but no, a plasma can also be a solid. So those things are not mutually exclusive. So when we say plasma, the only thing we mean is that the electrons are removed from the atoms. So you have ions and electrons separately, but that doesn't forbid them to be arranged into a solid structure. So all white dwarfs that we know of, and all white dwarfs that we believe exist today in our galaxy, are still way too hot to be at those very low temperatures of the background of the universe. The universe is simply too young yet to have produced what we could call black dwarfs. Sometimes that's used, so it's not very well defined as a term, but the idea is that you would be in thermal equilibrium with the cosmic microwave background. So those objects simply, as far as we know, they don't exist yet. And I mean, if they did exist, it would be a big surprise, and it would challenge lots of things in cosmology and so on.
Right. It would tell us the universe is significantly older than we thought. So then I want to talk about your research, and the reason that I reached out to you specifically was this, I guess, surprising discovery that white dwarfs are not cooling down at the rate that people think they should. Is that sort of the mystery in astronomy that you think you have a solution for? Yeah,
that's right. And I would say it even stronger than they cool down more slowly. It's that they essentially stop cooling. Many of them, so not all of them, but there's a specific population of massive white dwarfs that apparently just stop cooling for at least 8 billion years. So that's a lot. And well, it's as surprising as making a campfire and leaving it there, and then coming back a month later, and the embers are still bright hot. Like it should just cool down. So why is it still going on? So we know there's nothing left to burn inside the white dwarf. There is no thermonuclear burning going on because that was all before the white dwarf phase. So then, what can power their luminosity for so long? So that was really the conundrum. Maybe I can say a bit more before about the solution, about how we know that these white dwarfs stop cooling. Because if I look at a white dwarf today and I observe it again next year, I won't see a difference because the cooling process is over billions of years. So, a year is nothing. We can't measure the difference in temperature over that time span. So the way this was discovered, so this is thanks to data from the Gaia satellite from European Space Agency. So what Gaia does, it's very simple. It just measures the positions of stars in our galaxy, and it does this very, very precisely. And this allows us in turn to know the distances of all those white dwarfs, because you take measurements at different times of the years, and then you get a parallax, and from that you get a distance. Now, the distance is a big deal because it removes the degeneracy between the intrinsic brightness of the star and its distance from us. And so that allows us to measure the radii of white dwarfs. So you can make the difference between a bright white dwarf with a smaller radius or a fainter one with a larger radius. And by knowing all those properties, we can map those white dwarfs into the Hertzsprung-Russell diagram that astronomers like a lot. And when you do that, you expect to find all white dwarfs following a nice sequence that we call the cooling sequence, going from bright and hot to cool and dim. So we see that, but we also see a weird feature. So at some temperature along this cooling track, there is an accumulation of stars. Like you have fewer stars before, fewer stars after, and right there you have like a bunch of stars just piled up there. And so we can conclude from that the stars must slow their cooling process when they're at that temperature. Otherwise, we would not expect to see that many stars in that specific region of the HR diagram. So it's really like a traffic jam of white dwarfs. And then you can do a statistical analysis from that, and you conclude that they have to stop cooling down essentially for at least 8 billion years to explain those observations.
And that's a big chunk of time. I mean, that is a lot of white dwarfs are going to fall into this within 8 billion year range.
Yeah, that's correct. So this extra delay affects, we think, only. Well, we can go back to that after, but we know for sure that it affects the ultramassive white dwarfs that we call. So those are white dwarfs more massive than about 1.05 solar mass. And it affects something like 6% of them. But when we look at this accumulation of stars, we think that more than half of them are actually undergoing this delay, because if you have just 6% that stop, but they stop for so long, well, they accumulate there, while the other one, they just cool down, and at some point we don't see them anymore. Yeah.
So what do you think is the cause? What's causing this?
Yeah, so this was discovered in 2019, and then, well, as astrophysicists like to do, I mean, that's exactly the kind of thing we like to have. It's a nice puzzle. We have observations, something we can explain. So then you try to find a theory to explain that. So the theory we have now, and that seems to work very well, goes as follows. So we know that white dwarfs, as we've just discussed, crystallize at some point in their cooling process when they become cool enough. Now, this crystallization process starts at the very center of the star. So this might be a bit surprising because if we look at the Earth or the Sun, it's where the temperature is highest. So you might think, well, I mean, that's not where you will freeze first. But actually, the core of a white dwarf is almost isothermal, so the same temperature everywhere, because the density is so high that matter is really good at conducting heat very efficiently. So it's the same temperature, essentially. But at the center, it's much denser. And so this is what favors the freezing process. So you start with a little crystal at the center of the star, and then gradually, as the white dwarf cools down, you add like new layers on top of this crystal, and that takes a few billions of years. And then at the end, basically the whole white dwarf is frozen into a solid state. So this is the classical picture. And now what we've done is that we've looked in more details at what happens exactly when this crystal form, and in particular, how the composition of the crystal can be different from the composition of the fluid plasma around it. Because in general, if you take a mixture of different species and you freeze it, the solid phase does not have the same composition as the liquid phase. For example, if you look at ice formation on seawater, the salt is largely expelled from the solid phase. So you can melt sea ice and drink it, and that's fine. There's no salt. The salt just gets expelled in the liquid. So a very similar process is going on here in the white dwarfs, in the sense that we have our salt here is neon 22. So it's an isotope of neon that is present in white dwarfs, just a few percent, on top of the carbon and oxygen that makes most of it. And this neon 22 is expelled from the solid when the crystals are formed. But neon 22 is heavier, is much heavier than the carbon and the oxygen. And so as a result, the crystal that you form can be buoyant compared to the liquid. So they're less dense and they want to just float up. And so that means that the classical description of the crystal just starting at the center and then growing, from the inside out, cannot work in that situation, because the crystal won't stay at the center. It will just rise up and float. And by floating up, it will eventually melt, because you don't have the conditions for crystallizations that are met yet higher up in the star. But the key point is that by rising up, it has to displace liquid down to fill back the hole left behind. And this liquid, by definition, will be more dense, because the crystal expel the heavy stuff out of it. So you have this kind of convection-like motion where you have crystals rising up, liquid going down, but this liquid is heavier. So gradually you're pushing the heavier stuff towards the center of the star. Now, if you take heavy stuff and you put it down at the center of a gravitational energy well, you are releasing gravitational energy. And that energy is a new source of energy for the white dwarf. It's like a little heat engine. And this is what we think is keeping the luminosity of those stars constant for billions of years. So we've done the calculations, put that into stellar evolution codes, and it matches exactly what we see in the data.
And the evidence of this neon in the atmosphere and the upper layers of the star is evidence that in addition to these crystals of stellar material rising and falling, they're also expelling or bringing these additional metals with them.
So we cannot see the neon in the atmosphere. So this is one thing that's a bit annoying with white dwarfs, is that most of the masses, so this carbon and oxygen with the trace of neon, but on top of that, there's a layer of helium and a layer of hydrogen. They're very thin, but they are opaque enough that we don't see deeper than that. So we don't have a direct window into what's happening inside the star. So really, we have to just deduct all this from models of how the composition of the star looks like. The only window we have onto the interior of the white dwarf is asteroseismology. So there, the idea is that white dwarfs can pulsate like many other types of stars. And you can look at the frequencies at which this pulsation takes place. And from that, you can try to infer the composition inside the star. So this is... this, of course, validates that, there's carbon and there's oxygen in the core and that kind of thing. Now, in the future, it would be great to be able to do this kind of analysis for those white dwarfs that have this neon transport going on, because potentially we could see the signature of this process in the data. Unfortunately, it's not something we can do right now, mostly because it's already hard enough to do this for just normal white dwarfs. There's lots of uncertainties. It's not straightforward to transform those pulsation periods into like a composition profile for the star. But eventually that would be a way to really directly see this process. But for now, we have a process that is predicted by first principle physics, and that matches all the observations that we have. So that's pretty much as good as it gets, in astrophysics.
I mean, unfortunately, because it's such a hot object, you can't call upon James Webb to save the day the way
Um,
other astronomers can. Oh, maybe you can.
well, actually, there's something that we might be able to do. So, okay, so this process does not affect, we think, all white dwarfs in this very extreme way of causing this very large delay. So we think it's for those specific stars that we've studied now, it's they are most likely remnant of stellar mergers, where you have two stars merging and making a bigger white dwarf. And when this merging occurs, you have some nuclear reactions that create additional uh, neon 22 or magnesium 26 or other similar isotopes that we need for this process, because most white dwarfs just don't have enough neon to make this process, at least to make it as important. But there is some specific stellar populations that don't need a merger to have so much neon 22, and those are metal-rich populations. So there are globular clusters in our Milky Way where you have just more metals. That I mean, the stars were formed from a different environment, and then you have enough neon 22 to have this process going. And we have Hubble data for one of those very metal-rich cluster that really suggests. So if you look, so all the stars in a globular cluster have the same age, and so that means that if all the white dwarfs are delayed in their cooling, there will be a signature when you look at where the white dwarfs are in the HR diagram. And we think we see it in the HST data, but there's a lots of scatter in the data, just because those stars are very far away. White dwarfs are quite faint. But with James Webb, actually, we could really, really see it very well, just because James Webb, you can get much nicer signal to noise ratio with shorter observations.
And,
So this is yeah.
and those globular clusters, they are the oldest in the universe. So they're, I mean, I don't know, like what is the temperature of a 13 billion year old white dwarf?
So
I mean, are
that
they?
really it can be pretty much anything in a sense, because it really depends on the mass. So our sun, for example, will sit on the main sequence burning hydrogen for almost 10 billion years. And so that means, a total age of 13 billion years for a star the mass of our sun doesn't give you a white dwarf that is that cool. If you have a more massive star, then it zips much faster through stellar evolution, and then those stars basically there is no way we can see them today because they're very cool white dwarfs that are very hard to observe. So there's really a large
Oh,
continuum.
really? Okay. So there are white dwarfs that would be perfectly viable to search for them in the infrared spectrum with something like James Webb. If you knew where one of these might be, these candidate white dwarfs, it could be in the kind of temperature regime that James Webb is perfect to observe.
Oh yeah, absolutely. Yeah.
Oh,
Yeah.
interesting.
Yeah.
Okay.
Yeah.
Um,
Yeah.
so I want to shift gears a bit then and talk about this idea of the pollution of
Mm.
white dwarf atmospheres. And this is such a sort of awful way to describe this process. You say, "Oh, look at these white dwarf atmospheres; they're polluted." Well, what are they polluted by? They're polluted by shredded planets that have rained down onto the white dwarf. So, do we have a sense of how many of these white dwarfs out there have gobbled up their planets and are
Yeah.
getting sort of
It's actually
polluted by their
uh,
precious metals?
it sounds like a simple question, but it's actually a question that's hard to answer precisely. And the reason for that is when so you have those rock forming elements that we detect in the atmospheres of those white dwarfs, and so we don't expect to see them there because there is a very strong gravitational field. So everything should sink below the observable region of the star in a matter of, depending on the white dwarf, it can be in a matter of days to millions of years. But anyhow, this is very short compared to the life of a white dwarf. So we know this material arrived recently. But even if it arrived recently, it's still always slowly sinking down, diffusing below the region that we can see. And so that means that some white dwarfs, you will detect those metals in the spectrum very clearly. You take a spectrum and in the visible light, you see it very clearly. In some other, you will look in the visible light, you'll see nothing. Then you'll go with Hubble and you'll see nice spectral lines from rock forming elements in the UV part of the spectrum, because it's much easier to observe there. So it's really a question of where did you set the threshold for, is it polluted or is it not polluted? But it's somewhere around 25 to 50% of white dwarfs that have recently accreted
Whoa.
planetary material, in the sense that we can observe it with the proper tools. Yeah,
That seems like a lot.
yeah, it's a lot, and
Seems
I
like a high
mean,
number, yeah.
it's so it's not only planets. Probably most of them, it's smaller things, asteroids or comets. You really don't need a lot of pollution before we see it, because the atmosphere otherwise is essentially pure hydrogen. It's very pristine. So the kind of pollution that you need is of the order of 1 part per 10 billion. And then we see nice spectral lines. So you really need a tiny quantity to see it. So we're quite sensitive.
Now, the hope is that maybe even though the star has died, turned into a red giant, consumed its inner planets, and then threw off its outer layers, and you're left with the white dwarf, that maybe, just maybe, planets can survive. And so this clearly is indication that something survives. What do you think about like the long-term prospects of planets, maybe even the habitable zone around the white dwarf?
Yeah, well, we know that some planets do survive. We have a few white dwarf system where we have detected planets, gas giants, and so we know that this is perfectly possible. And there are many. I know of many James Webb programs right now that are looking exactly at that. So trying to detect more planets around white dwarfs. So it's totally possible. Then. Of course, the architecture of the planetary system is completely disrupted when you go from to the red giant phase and all that before becoming a white dwarf. So there's a lot of open questions about all the planetary dynamics aspects of how those systems evolve. So there's probably lots of migration of different planets. And so that's an open question. Now, another aspect of this research, I think, is that's very important to mention, is that we're not just finding that there are planets, but when the white dwarf accretes planetary material, we can actually find the composition of the rocks that made up those planets. And that's really the cool, unique thing that white dwarfs are bringing to the exoplanet field.
That's horrible.
Because we can start doing geochemistry, basically. So you can look at the ratio of different elements, magnesium, calcium, oxygen,
Yeah.
that kind of thing, and find out, well, was this thing something like a comet with lots of volatiles, or was it closer to an asteroid with less volatile compounds? In some cases, we can see hints that there probably was water on those bodies that were accreted, because you have too much oxygen that you can. So you have like some quantity of oxygen, and then you have all the other elements, and you can make this budget where you put the oxygen with the iron and some with the magnesium to make all the oxides that are formed in rocks, and then you're left with a bunch of oxygen. So then you conclude, well, probably that's from water. So there's lots of cool things we can do with that. Of course, those are now dead planets or dead asteroids or whatever. So it's less exciting than an actual world that exists right now. But that still brings very interesting constraints about just what's out there that's different from what we have here. Because all the other methods to measure the composition of exoplanets, it's either just looking at the atmosphere or trying to deduct the composition just from the mass and radius of the planet. So you get a density for the planet, and from that you try to see what fits this density. But of course, it's highly degenerate. Like, you can have many different things of the same density. So yeah, white dwarfs are a nice addition to this toolkit.
That's really interesting, and as I said, it's kind of horrible that we're going to learn more about the composition of exoplanets as we watch them splat into white dwarfs
Yeah.
and detect the wreckage and go, oh, well, luckily now the entire planet has been spread out in a way that we can see all of the elements. Oh, it's got a lot of magnesium. That's interesting, which is not the kinds of observations that you can make just looking at the atmosphere. And so that's really, really interesting. So does the need to observe white dwarfs better, what would be sort of in your mind if the here in Canada, if the National Research Council got together and decided we're going to build the Canadian White Dwarf telescope, and it was going to be the perfect telescope for this job? What kind of a telescope would really give you a better way of observing white dwarfs, do you think?
Um, well, actually, I will start by saying that the National Research Council and other universities are actually planning and I'm part of this, a Canadian Space Telescope. So, and it
But it's
will
not the
actually,
Canadian White Dwarf telescope, is
well,
it?
it's not specifically for white dwarfs, but there are many attributes that I can say that will be very useful for white dwarfs. And the main one is that it's going to look in the UV. And in the UV, there's just lots of things we can do with white dwarfs, especially regarding this metal pollution. It's just so much easier to detect in the UV than in the optical. And Hubble will go away at some point. And so that's really the capacity that we need for this kind of science. Um, then I'm not sure I can design as like the ideal instrument. I want many instruments because like this kind of stuff you need the UV. But for other things I'm interested in, like the very oldest and coolest white dwarfs, then you're better off with something like James Webb, looking in the infrared, because they're cooler, so things happen more in the infrared. And actually, so right now I'm analyzing data from James Webb for what we call ultra cool white dwarfs. So those are white dwarfs that are so cool. So normally when you cool down, the light goes from being mostly blue to being mostly red, and then the infrared. But those white dwarfs are so cool that instead of just going towards the red, it goes back towards the blue at some point. And the reason it goes back towards the blue is that you have molecules, hydrogen molecules, in the atmosphere that block the light in the infrared. And so even though you would want to have mostly light in the infrared, it gets redistributed towards the blue when they become very cool. And our models for these stars are horrible. They really don't work well. So we're trying to fine tune them using this James Webb data, and it's very important because those are the oldest white dwarfs out there. Um, and so yeah, and so that's important because we use white dwarfs. I mean, this is something I should have mentioned earlier, but a big use of white dwarfs in astronomy is to use them as cosmic clocks. So white dwarfs cool down with time. And so the cooler they are, the older they are. So if you measure the temperatures of white dwarfs throughout our galaxy, you can then make a map of the ages of different regions of our galaxy and better understand how it was formed. But of course, to do that, you need a good model of how fast they cool down. And so this is why this kind of research is important for many other areas of astronomy. So I know I didn't give a good answer to what would be
Yeah,
my ideal telescope. But,
I'm kind of envisioning, I guess, something that is more powerful than James Webb and Hubble, maybe a 20-meter space telescope, but also has a much wider wavelength range. You can go from ultraviolet through visible to infrared. So you're kind of describing LUVOIR, I guess,
yeah,
would be the telescope that you
yeah,
would want.
yeah,
So, but only for white dwarfs. So that's all. I mean, really narrow field of view, no other purpose. But yeah, like just a general purpose telescope that you can observe at different wavelengths is great. So I think in this case, you're probably, you and the rest of the white dwarf researchers are easy to please because you just want a great big telescope that lets you observe in different wavelengths. So
yeah, pretty
ideally
much. I mean, there's
ultraviolet.
stuff to
Yeah.
do in different areas. So yeah.
Yeah, no, that all sounds great. I guess the last thing I want to talk about is, we're talking about white dwarfs on their own, but many, many white dwarfs. You mentioned mergers. We know that white dwarfs are actively feeding off of their binary companions and will inevitably become type 1a supernovae. So how do you think about not just these things all by themselves, but in the dynamics of interactions with other stars? How does that change your thinking about white dwarfs?
Yeah. So white dwarfs are well known as the progenitors of what's called type 1a supernovae. So this is when a white dwarf accretes mass from a companion and eventually explode. And that's super useful because there's some calibration between the brightness of this explosion and the time it takes for the light curve to kind of fade away. And so this is used to measure distance, to other galaxies and stuff. And so there's lots of this has always been a good motivation for studying white dwarfs. Now, what's interesting with those findings with the crystallization of white dwarfs is that you redistribute how the chemical species are placed inside the star. And so when you have this thermonuclear explosion, you're not burning exactly the same material, and so that's changing a bit, like the output of this explosion, like which isotopes exactly are you creating and that kind of thing. And so this is something I know that many people are currently looking at, like what is the consequence of having this neon redistribution in the star. And so I hope to see more of that research soon, like how exactly does it affect the type 1a supernova explosions.
Do you think it's enough to start to explain, say, the crisis in cosmology, the Hubble tension, where maybe you can't assume that all type 1a supernovae are the same luminosity?
Yeah, I would be surprised if it would make such a difference. I think the difference will mostly be for the chemical output of the explosion. So those explosions are responsible for creating lots of the elements, that we see. So I think that would more be on this side than on the brightness side. But
right. Simon, what are you obsessed with right now?
What am I obsessed with? So all this about white dwarf cooling and stuff, it really depends on what's the actual composition of the star. And as I've explained, we can't really directly observe it. So what I'm doing right now at the University of Victoria is we're performing large-scale 3D hydrodynamic simulations of the interiors of white dwarf progenitors. So those are really big computer simulations. We run that on some of the biggest supercomputers in North America. And we're resolving the motion of fluid inside stars. So you have convections and you have waves, and we're resolving that to better understand how things burn before the white dwarf phase, to then have a better picture of like what's the actual composition of the white dwarf. So it's a whole area in itself, but it's really fun and it makes nice movies.
Yeah.
So it's pretty cool.
And so giving you a sense of how the size, the shape, the internal processes of the star in the end will lead to the white dwarf.
Exactly. So the big questions are related to chemical mixing. So, for example, before the white dwarf phase, you are burning helium in the core of a red giant, and this core is convective, so things move a lot. And there's a question of how much mixing do you have at the interface of this helium burning core and the envelope above it. So like in our traditional model, we assume there's a sharp cutoff, like this is all mixed and then this is not mixed at all. But what we see in the simulations is actually much more dynamic than that. You have those waves that propagate through the stars and can cause mixing. So this is the kind of questions we're trying to answer. So for a long time, all models of the evolution of stars have been what we call one-dimensional. So you just have the only dimension is the radius. So you go from the center to the surface. A star, of course, is not one-dimensional. It's three-dimensional, and there's lots of things that happen in 3 dimension that you don't have in 1 dimension. So this is kind of what we're trying to patch in our models, basically.
Oh, it all sounds really fascinating. Simon, thank you so much for taking the time to chat with me today, and good luck with your research.
Thank you. That was fun.
I hope you enjoyed that conversation about white dwarfs with Dr. Simon Blouin. I'm going to talk a little bit more about white dwarfs for a second, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Antonio Lofilara, David Gildenan, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, Stephen Filer-Munley, and Vlad Chiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I really see a theme here with these observations about white dwarfs. What you imagine is this gigantic crystal diamond in space. Okay, not a diamond in space, actually very complicated with blobs of crystal forming down at the core of the star and then floating up through these layers, reaching close to the surface, melting, breaking apart, falling back down. Like, this does not feel like a dead star. And yet this is the kind of future that the sun has in it. And then when you think about, okay, you've got this this pause in temperature cooling for 8 billion years, that's a long time. And if you could end up and have a terrestrial planet end up in the habitable zone around one of these stars, and there wasn't a lot of other things going on, that's a relatively comfortable existence with a long-term future. You're not going to get the same kind of heating up that we experience. So I wonder, does this make white dwarfs more interesting, more habitable candidates as places where we could be searching for life in the future? Or are they still tearing these planets apart, gobbling them up? They're not a good place to live. So as always, I'll keep you posted as we learn more about white dwarfs. Now, I've done a bunch of other interviews about white dwarfs, so I'll link a couple of them here. All right, we'll see you next time.